Here we're considering a jet propulsion cycle with a gas turbine. We're given a turbojet engine with these parameters, and we're asked to find the propulsive efficiency. Here's our standard assumptions with constant specific heat and the cycle we're using. So here's the Brayton cycle, starting with our lower pressure going into the diffuser from state 1 to state 2. We apply the first law of thermodynamics here. We expand our equation to have all of the terms. So our heat, our work, our enthalpy, our kinetic energy terms, and finally our potential energy terms. Now most of these can be eliminated because in the diffuser these values are 0. So our first law simplifies down to this equation here. Since we have constant specific heats, we can convert these enthalpies to temperatures, and since we know T1 and V1, we can solve for T2. So when we solve this equation, we get T2 is equal to 297 Kelvin. Since this is an ideal diffuser, we assume that entropy is constant. And using our isotropic formula, we can calculate the pressure at state 2, the inlet to the gas, or the inlet to the compressor. Now for the compressor, we know our pressure ratio. So then we can solve for T3 since we know T2. So then we get T3 is equal to 442 Kelvin. Taking the difference of the temperatures multiplying by the heat capacity, we can find out the work done by the compressor. So the compressor work is equal to about 163.9 kilojoules per kilogram. Now we're given state 4 temperature, so using T4 and T3 we can calculate Qin that comes from the combustion chamber. So Qin is about 761.4 kilojoules per kilogram. Now doing a control of volume around the gas turbine, we know that the turbine's only driving the compressor, so then we can equate the work from the turbine to the work from the compressor. This allows us to solve for temperature at state 5. Then we get temperature at state 5 is equal to 1037 Kelvin. Since it's an isentropic process, we can use this formula to find the pressure at state 5. That's the turbine exit pressure. Finally, the gas is accelerated and expanded out through the nozzle. So we know that P6 is the atmospheric pressure at the altitude we're working at, and that's 55 kilopascals. So we know our pressure ratio, therefore we can find the exit temperature. And using a control volume, the first law of thermodynamics around the nozzle, we can then solve for the exit velocity. We know our heat capacity, we know the two temperatures at state 5 and state 6, and therefore we find 832.4 meters per second is the velocity exited out the nozzle. To find the thrust, we multiply the mass flow rate of air by the change in velocity, and we're given the mass flow rate of air in the problem. and we can find the difference in velocity, and then we get about 27.5 kilonewtons of thrust. To get the propulsive power, you multiply the thrust by the velocity of the aircraft, and we get the propulsive power is about 6 megawatts. The propulsive efficiency is the propulsive power divided by the heat input. So we have about 6,000 kilowatts divided by Qn, and we have to include the mass flow rate in the denominator. So we get the propulsive efficiency of about 17.7% for the cycle.